Hello everyone, I'm Qianshan from Tsinghua University. I am glad to present our recent work in regression verification. The title is Incremental Predicate Analysis for Regression Verification. Let me introduce the problems first. Due to performance improvement, new features, or even bug fixes, software is constantly evolving in its life cycles. The picture shows the timeline of Linux kernel. Over the past 30 years, the Linux kernel has evolved in many versions. Another problem is about predicate analysis. Predicate analysis is a practical approach for program verification. It tracks the set of predicates and computes evaluation at each program location. Finally, it checks if the error location is reached or not. If it is reached, we say that this program is safe. Otherwise, the program is unsafe, and the predicate analysis will return a counterexample. However, predicate analysis can only cooperate a single program at present. To exploit the advantages of predicate analysis in the evolving software, the following research question needs to be addressed. That is, how to apply the predicate analysis to multiple software revisions. Let's look at an example. This is a simple program and its control flow automaton. In the figure on the right, the nodes represent the program locations and the edges are labeled by program statements. The program contains a do-while loop, and after the loop, it checks if I is greater than or equal to n. And at line 8, it checks if the property new equal to old stands. Now we conduct the predicate analysis on this program. The tracked predicates are new equal to old and I less than n. And this is the result of predicate analysis. In this figure, we use a hollow dot to represent the predicate new equal to old, and the solid dot to represent the predicate I less than n. The formula in the error location is bottom, which means this program is safe. Given a program, the individual verification of it can be considered as a process of constructing assertion annotation. In this example, after predicate analysis with the tracked predicates, the annotation is shown in the right side. The number of assertions is limited by the number of locations in the program. It's quite compact for storing and efficient for processing. Now in this example, a new version has evolved. The line 3 to line 4 in the older version are replaced by line 3.1 to line 4. We want to make the predicate analysis deal with this program's two revisions. Assume the revision P has already been verified. Our motivation is to reuse the previous generated assertion annotation of P. This is the framework of our incremental predicate analysis. The basic idea is to construct an initial annotation for Q by reusing the previously generated annotation for P. Due to program changes, not all assertions of P can apply to Q. In order to figure out the differences between the two versions P and Q, we design the algorithm CFA Diff. In this picture, the input is colored in orange and the output is colored in blue. The outputs of this algorithm are the set of changed edges, and the location mapping between the control flow automata of a revision P and Q. Next, as we have got the program differences, we need to investigate how the differences impact other parts of a program statements. The change impact analysis algorithm takes a set of changed edges as input. It propagates the impact of program changes according to the dependencies of program statements and computes the set of impacted variables at each location of Q. Now, we rely on the location mapping and the set of impacted variables to determine if an assertion of P called IP can be reused in Q or not. The reuse annotation algorithm computes an initial annotation IQ minus for program Q. Finally, the incremental predicate analysis algorithm takes the program Q and an initial annotation IQ minus as inputs. It returns either safe with a certified annotation I or unsafe with a feasible abstract counterexample. The standard predicate analysis can be seen as a special case of this algorithm. Let me introduce the details of CFA Diff first. To compute the program differences, we implement the CFA Diff algorithm based on the similarity flooding algorithm. The link below is the code that we rely on. CF Diff takes the control flow automata of two program versions as input and identifies the syntactic differences between the two automata. The algorithm builds a mapping of program locations from the new version Q to the old version P and identifies the changed edges across the evolution. We use this example to show how the CFDiff algorithm works. Given two control flow automata P and Q, this is a location mapping from Q to P that we build. The mapping is established based on similarity flooding algorithm, which is a graph-based similarity comparison algorithm. Note that in this example, the two locations in green of program Q are new locations. And then, after getting the location mapping, it's easy to obtain the changed edges. As shown in the figure, there are 4 edges identified as changed, including 3 added edges and 1 modified edge from L4 to L5. Now, let me introduce the change impact analysis algorithm. We first compute all the impacted edges by the changed edges using the fold slicing technique, specifically for each edge in the changed edges. We analyze the set of impacted edges and then compute their union set. In this example, there are 4 changed edges, and after analyzing the impact of them, 3 more edges are identified as impacted, are those turning right in the figure. In order to get the potential affected variables at each program location, we attach the variables of a changed edge to its subsequent location. For the edge with a sum statement, we attach all the variables occurs in it, and for the edge with a summand statement, we attach its left side variable. The animation shows this process. Note that if more than one edge have the same successor, we take the union set. And then we need to propagate the impacted variables to a fixed point. In the propagation process, each location will combine all the impacted variables of its predecessors. The animation presents the whole propagation process. Finally, we get the set of impacted variables. The set is computed conservatively such that it is a subset of semantically impacted variables. We thus can safely use the set to find the non-impacted variables at each program location, which can help us to reuse the assertions. The goal of the reuse annotation algorithm is to construct the initial annotation IQ- with the help of the set of impacted variables. Up to now, we have the old version program P and its assertion annotation. We get the location mapping and the changed eyes by CFA Diff algorithm, and we have the set of impacted variables for every program location by changing impact analysis. We want to reuse the unaffected assertions for the old program version. Firstly, the assertions can map according to the location mapping. The assertions in green are unaffected and can be safely reused. Recall that the impacted variable at location L7 is I and Q. The assertion in orange is potentially affected by the variable I. So we need to strengthen this assertion to remove the impacted part in the formula. Finally, we get the initial annotation for program Q. Now we perform the incremental predicate analysis. The figure on the left shows the new version program and the reused annotation. IPA algorithm takes the reused annotation as input. Note that the annotation of a program location represents the set of all reachable abstract states at that location. IPA initializes the state space by the reused annotation and conducts the standard predicate analysis then. As a comparison, the classical predicate analysis starts with an empty state space. Finally, IPA returns either safe with a certified annotation or unsafe with a feasible abstract counterexample. Let's look at the evaluation part. Our benchmark is publicly available. Below is a link. It consists of 1,119 revisions of 62 Linux device drivers and totally 4,193 tasks. We implement our approach on top of CPU check, which is a state-of-the-art software verification tool. The table below summarizes the experimental result of our incremental predicate analysis and the classical predicate analysis. Overall, IPA achieved 2.8 times speedup in total time and solved additional 393 tasks. In this page, these diagrams compare PA and IPA in total time, number of abstract states, and memory usage. The crosses above the diagonal indicate that IPA is better than PA. In short, IPA requires less time, less abstract states, and less memory usage compared to PA in most tasks. The pie chart in this page presents a distribution of analysis time for the 393 tasks. The majority of them take less than 1 minute. About 80% of tasks need more than 2 minutes to solve. This chart demonstrates the efficiency of IPA on tasks unsolved by PA within 300 time limit. Now, let's make a summary. We use assertion annotations as intermediate results for regression verification. We propose a lightweight impact analysis and strengthening techniques for reusing assertions. We propose an incremental predicate analysis technique for involving programs and prove its soundness. We implement our algorithms on top of CPA check and report extensive experiments on revisions of Linux kernel drivers. Thanks for listening. Please feel free to ask questions.